Hello, I'm Roman, and welcome back to the series of the videos called Neural Networks from Scratch, where we dive into the bare bones of the neural networks. And again, I'm using this book called Neural Networks from Scratch in Python, but I rewrite everything in a Golang. And I would tell this, I have a terrible headache today, so I'm not sure if I will manage to record 1 hour as I'm usually doing, because like the next thing I need to dive into what is the Softmax activation function. I don't think it's not that much of the code again, but I don't know. My commitment is to do 6 hours per week, so I will have only 1 day without the recording. So yeah, let's try. In the previous video, we took a look on different activation functions, and specifically we activated the rectified linear unit activation function. So right now we have this small struct that basically takes an inputs and checks if the value is bigger than 0, then it stores the value. Otherwise, it just puts 0, and that's it. And right now, what we have is we have a generated data for inputs. We have the first layer that has the forward function, and then we create the activation ReLU, and the forward will just wait. And forward. Okay, I'm not sure, but specifically with the activation, forward is the Go PLS. I think the Go PLS cannot find the what's called the struct, but it works okay. So it cannot. There is an issue with the activation, but for example, if I take a look at the forward from the jump to location. Okay, for some reason the jump to location doesn't work anymore, so maybe there is something is broken with the latest plugins update, but I will take a look at this later, because what I can do, not this one, for example, forward, I could, use the LSP dynamic workspace symbols and check it like this, and that will actually go through all of the dependencies for this project. But okay, let's go through the Softmax. And the Softmax is another activation function, but I assume that we will use it for the output layer, which we don't have. But yeah, for example, we can create the second layer of the values. Okay. Why we're bothering with another activation function? Yeah, that's true. It just depends on what our overall goals are. So again, in the future, I guess we will be using different activation functions for different purposes. I guess for this one, the rectified linear unit is unbounded, not normalized with other units and exclusive. So it means that non-normalized, we could have very different values. And to address the lack of the softmax activation function on the output data, can take in non-normalized or uncalibrated inputs and produce a normalized distribution of probabilities for our cases. So I assume that the goal of the softmax, and I'm taking a look at the formula here, so we will have some value divided by the sum of the possible values. So we will have something like from 0 to 1. This distribution returned by the softmax activation function represents confidence scores for each class, and we will add up to 1. The predicted class is associated with the output neuron that returns the largest confidence score. And for example, if we're creating the neural network that tries to predict two different classes, it could have the probabilities like this. And actually, in that case, the probabilities are very close to each other, and it means that this is the very low probability of the class. It kind of thinks that it's a second class, but the probability is very low, meaning that the neural network is not accurate, not that confident, right? So that describes what's the exponentiate. So basically this is the function that uses the Euler's number, which is 2.7, and it's referred to as exponential growth number. And basically you're taking this number and making it in power of the x value. So for example, if this is the e, you can also use math.e. I think the math package or Go numpad should have something like this. We can try to search for it. Looks like mathematical const. Yeah, we have E, P, B. So we have a couple of predefined values and they math const. Okay, I guess we'll just use it. For each value in vector, calculate the exponential value. So we take all of the kind of layer outputs, which will be the input for the softmax. We calculate the exponential value for each one, and we have this chain of the big numbers. Exponent change asserts multiple properties. To calculate the probabilities, we need non-negative values, because probability cannot be 0. Imagine the output as, and we have something negative. Even after normalization, the last value will still be negative, since we'll just divide all of them by their sum. Yes, because, for example, if we sum up all of this, it will be the positive value, but this one is negative, so you divide negative on the positive, you get the negative number. Exponential value of any number is always non-negative. It returns 0 for negativity value and 1 for the... So it's like this. Yeah, and the reason for this, if you have the negative, if you have the constant, the positive const value, and you have the negative power, it means that the value will be in between 0 and 1. But it's still like the result, it still will be the positive value itself. So this is the way to turn a negative number into the positive number. And the exponential function is a monotonic function. This means that with the higher input values, outputs are also higher. Yeah, the higher the x value, the higher the output. Since each output value normalizes to the fraction of the sum, all of the values are now in the range of 0 to 1. So the idea is that we calculate the x values for everything, then we take a sum, so that will be our base, and then we calculate the fraction, corresponding action to the sum, of the value to the sum. And this is how we end up, for example, this is the biggest value, and that was this one. So this is very, relatively small than this one. This one is this one is closer to this one rather than to the first element, and we can see this after the normalization. So this is the lowest value. It is very far away from the first one, and this is much closer to this one than the first one. And the sum of the normalized values are 1, which is expected, because, for example, if we have a classifier of 10, we have any we have a classifier that returns probability for any amount of the probabilities, or any amount of the categories. The sum of the probabilities should be 100%, because you distribute your confidence between different classes. For example, you are very confident that this one is, I don't know, the first class, and the probabilities for the rest will be very, very small. They still will be non-zero, but they actually might be even zeros. We can perform the same set of operation with the use of NumPy in the following way. To train in batches, we need to convert this functionality to accept layer output in batches. It's actually interesting. Maybe I made a mistake here, but no, maybe not. Oh no, here it's just check all of the values, but for this one, because we'll be doing the batching, so we get the exponential value, then we have the probabilities, normalize them for each sample. It means that, for example, we have a rows as the input, and when we will have columns as neurons. So this is the same as we define the inputs. And we have some new functions. Specifically, NP does the exponentiation. We should also address what axis and keep dims means. Let's first discuss the axis. Axis is easier to show than tell, but in 2D array matrix, axis 0 refers to the rows, axis 1 refers to the columns. Let's see some examples of how axis affects the sum using the NumPy. Okay, if we don't define the axis, it will just sum everything, but I guess if you define the axis, it means that it will make a sum. Another way to think of it is a matrix equals to the columns. We want sum of the rows. You can probably guess how to do it with NumPy, but we will still show the from the scratch version. For I in layer sum. Okay, but we want... So we can sum axis 1, but not that current shape. Okay, let's take a look. Okay, 8. Okay, so this code, what it means, it returns an array where the first element is the sum of the first row, right? Keep dimensions. With this, we keep the same dimensions as the input. Now, if we divide the array containing a batch of the of outputs with this array, NumPy will perform this sample-wise. That means that it will divide all of the values from each output by the corresponding row from the sample, since this... Yeah, okay. Finally, we also included a subtraction of the largest of the inputs. Before we did the exponent change, there are two main pervasive challenges with neural networks: dead neurons and very large numbers, referred to as exploding values. Dead neurons are enormous numbers, can wreak havoc down the line and render a network less over time. The exponential function used in softmax activation is one of the sources of exploding values. Let's see some examples of how and why this could easily happen. Okay. It doesn't take a very large number in this case. No referral. Okay. We can use this property to prevent the exponential function from overflow. Suppose we subtract the maximum value from a list. We would then change the output values to always be in a range from some negative value up to 0, as the largest number subtracted by itself returns 0. And any smaller number subtracted by it, yes, exactly the range discussed above. We saw max sense the normalization can subtract any value from all of the input and it will not change the output. The output confidence have changed due to non-linearity nature of... We can add another dense layer as the output layer, setting it to contain as many inputs as the previous layer has outputs, and as many outputs as our data includes cases. Then we can apply it. Create a second dense layer with 3x3 inputs feature, as we take out of the previous and 3 output values. Create softmax activation to be used with the dense layer. Make a forward pass. Make a forward pass through the activation function. We'll take the dense output. So then we use make a forward path through activation function. It takes the output of the second. As you can see, the distribution of predictions is almost equal as each of the sample has. Which classification the model has chance to predict, we perform an argmax. Okay, so actually I will try to code this. So the next thing is I need to calculate, I need to write, well, first let's create the second layer, right? layer 2, layer 1, 3, 3, then layer 2, and we take in the real 1 output, right? And then to do soft, and then we're making this softmax. Let's take a look if it works. Yes. Position forwards, okay. Put here, here. Layer 2. Okay, so we have something. Now let's create the softmax. Type activation, and it will have the, again, yes. Go now, then Softmax. Okay. Okay, so the first thing we need to allocate stuff, right? And that should be the same. No, wait. Okay, so we will have rows 100 and columns as the number of inputs, right? And what we going to do? Probably the code that I will write won't be efficient at all. Okay, so we need to go through the rows, right? So we going through the rows. And first we need to find max value. Second, subtract max value from a row, then x the value, right? And then x all values in a row, sum, and normalize. Interesting. Can I do something like, I don't know, row, dance, just new dance, 1C, and can I take the slice, like inputs, row, matrix, data, something like I multiply it by R and I multiply it by R plus C. How I can take the slice of an array? Go float, take slice range. No, I want to take with like this. No, I need, like, I want to take the sub slice, go and sub slice. Well, let's see if it works, because that means that I can take max. I can't take, no? I cannot take the max value? Come on. Max. Max the turn the, okay, but it, okay, maybe I can do this. Max, no. Go on metrics, the package math, the metrics. Oh, max. Oh, I just need, okay. Max T, right? What do you mean undefined max? Local goal slices sort. Okay, matrix. Max. It feels like I don't have the C matrix, but constants, diagonal arithmetics. Oh, here the max. Okay. And I should have max. No. Transpose and transpose. Dims at. Max return the largest element. Okay. But it takes the matrix. Row. Okay. Yeah. Okay. We found the max value. Then what we want to do, we want to sub. I cannot subtract the matrix A, B from A, placing the result into the receiver. So I should return the new matrix that shares But it will share, right? It will share data. Okay. I'm not feeling it, but okay. The headache is terrible, so what I'm going to do, I'm going to stop for today, but actually, I mean, probably I will need to make new dance or slice, I don't know. Because if I will take like how I tried, I mean, I need to create the new one because I need to copy. So then copy data from original inputs. Then we can find the max data, max value, then subtract because we'll be changing the copy. If I will continue how I tried to continue, I will mess with the original data, then exponents all the values in a row, and then do stuff like this. Okay, I will stop for today. This headache is killing me, and yeah. I see you tomorrow. Hopefully I will have a better sleep. I will not have that headache. I took a painkiller and it's still terrible. Yeah. See you tomorrow. Bye bye.